All right, well, welcome everyone. I am Katie Martinez. I am a T-Cube national instructor. I live in San Diego and teach at a public high school. And I have the privilege of piloting AP Precalculus for my district this year and participating in today's conference. So I'm really excited. I'm in the depths of it, like many of you, probably all of you. So thank you for allowing us to come on today and share some of our stuff with you. Todd, do you want to introduce yourself?
Sure. Hi, everybody. I'm Todd Steckler. I live in McAllen, Texas, down in the southern tip. Katie and I know each other for a long time. I actually came into T-Cubed in 2012, and Katie was one of our trainers along with Dan Ilaria. So we go back a ways. And so I'm also teaching AP Precalculus this summer. I had the pleasure of working with lots of teachers doing some APSIs around the country, and so now I'm excited to work with all of you here today.
Awesome. So we have a few activities that we're going to go through today. We're hoping to get through some sinusoidal transformations with cosine and tangent. We're going to look at a sinusoidal regression problem, as well as some equations, expressions, looking at equivalence there, and looking at polar functions, looking at polar rates of change and how to graph polar functions using technology so that we can explore those topics as well. So today's session is focused all around Unit 3 of our AP Precalculus content. So going through, just a reminder, there is the CED, the course and exam description. So hopefully you all have seen it. You probably have memorized many parts of it by now. So that's always our go-to for this course. We have these main concepts that we're looking at within Unit 3. So we have trigonometric functions and their transformations. As we know, transformations are embedded into all of our functions, and really looking in depth at those transformations. We have equivalent expressions with trigonometric functions. So I would probably expect that to appear on many multiple choice questions, possibly the fourth free response question, and then polar functions and rates of change. These are sort of our main topics there for Unit 3. And then they're broken down into little subsets. So this is what we're calling 3A. You can see it's all about sinusoidal functions, transformations, looking at data and contextual modeling. The second part, we're looking at tangent, inverse trig functions, as well as secant, cosecant, and cotangent functions and those equivalent relationships within trig. And then the third part is all about polar. So polar functions, their graphs, their features, looking at rates of change in polar functions. And we're hoping to get to that as well with a little activity today. Go ahead.
Okay, so we'll move into the math practices. Before I look at the math practices, I just want everybody to know we're going to try to use both Nspire and 84 today. So we'll be doing some back and forth. Everything that we can do on the Nspire, we can certainly do on the 84. Not everything that we can do. I said that wrong. So everything we can do on the 84, we can do on the Nspire. Not everything that we can do on the Nspire, we can do on the 84. But we'll try to, when we get there, we'll talk about how you could modify it with the 84. So the math practices, 1A, solving equations and inequalities. So we will definitely look at that with solving some trig equations. We might have some time to do a polar equation. Constructing some new functions, we will look at transformations of a sinusoid and also of a tangent function. We'll do some regression today on 1.3, constructing new functions. So those are for math practice 1, those are the two that we'll be focusing on with technology today. And then for math practice number 2, identifying information from graphs, we will not really be constructing a model other than doing a regression. We will do some transformations given a model, but we won't be constructing it. Constructing equivalent relationships, we'll do a little bit of work with that in 2.B for multiple representations. And then for communication and reasoning, somebody said this summer, and it made a lot of sense, that when students are working on the free response part of the test with the calculator, whenever there's a communication part of it, that might be a good time to just put the communication off when we don't have the calculator. So that's some advice that was given to us, and I think that's right on. So that takes care of our math practices.
And then some details about the test. As we all know, it's split into multiple choice and free response. So you can see here the exam weighting by unit. And so, like I said, unit 3 is what we're focusing on, trigonometric and polar functions. And that's going to be 30 to 35% of the multiple choice exam weighting. So that's a really big chunk, obviously a very important component of our test. And so thinking about how can we embed technology, how can we bring out the best of our students' understanding and enhancing their understanding with the technology in our trigonometric and polar functions units. And then our multiple choice section, there's that 30 to 35% right there at the bottom. We know that part A of the multiple choice, which is the calculator not permitted section, will be 28 questions, and the graphing calculator required section has 12 multiple choice questions. And so the free response section, we have 4 questions. Our trigonometry is really going to, in polar functions, will really come heavily into play in that last chunk, the calculator not permitted section. Question 3 is all about modeling in a periodic context. And so our first activity, we're going to explore how can we help the technology, how can the technology help us explore that and assist our students in visualizing the relationships there. And then question 4 is all about symbolic manipulation. So that could be any symbolic manipulation. I'm going to take a guess, there'll probably be some trigonometry in there. And that last part there, 2 questions, 30 minutes, and that's 18.75% of the test. We're going to look quickly at using technology in unit 3.
And so these are some different things that students should be expected to do with a calculator. Of course, perform calculations, graphing functions, analyzing graphs, generating a table, finding zeros of functions, intersection points, max and min, some numerical solutions with solvers, and then also with intersections, getting regression equations, and we'll focus in on sinusoidal today. And we'll even look at some residuals today.
Yeah, so hopefully if you're teaching AP Precalc, hopefully you've already started to embed the technology because it really does apply to everything. And so we're going to look at some of these features as we go through, really kind of pick out what can we do and when would it be appropriate to use the technology. That's sort of our overview of unit 3. So we're going to dive into our first activity. Let me pull up, we're going to do this on the 84. Am I correct there, Tom?
Yes, T84 with the sinusoidal function.
All right.
And so the function that we're going to do a transformation on, our parent function, is the cosine function. So the specific function equation that we're going to look at is f of x equals -6 cosine of 1/3 x.
1 second while I get that typed in.
There we go. 1/3 x minus pi, close parentheses, and then plus 4. And so we're going to do this using kind of an idea with pre-image points and image points. And so Katie wrote a little program just to save us a little bit of time for the pre-image points. And so the pre-image points for cosine, we're using the quadrantal angles, and the quadrantal angles at angle 0. We have cosine of 0 is 1, and then pi over 2 is 0, and pi is -1. 3 pi over 2 is 0, and then at 2 pi it's back to 1. And what we're going to look at is we're actually going to look at 2 periods. And the reason we're doing this is on free response question number 3, they actually give us 2 periods. So we're going to have, on that question, we're going to have to find the 5 points, the 5 transformation points off of those original that I talked about. And then also they give us a second period. So for this one, the second period we're going to look at is going to go from -2 pi to 0. So maybe Katie, if you can turn this graph off just to see how those pre-image points look on that graph.
Zoom 9.
And so those are the pre-image points here where we have 0, pi over 2, pi, 3 pi over 2, and 2 pi for the angles. And then reflecting that on the y-axis, we have -2 pi, a -3 pi over 2, -pi, -pi over 2, and 0. And so now if we go back to a y equals at our equation, so we're going to kind of look at something that is pretty similar to what Brian Passwater's been doing if you've ever looked at any of his stuff on transformations. So the first part we're going to work with is factoring out, if you will, our b, our coefficient of the x term here. So we'll factor the 1/3 out, and as we factor out the 1/3, we'll be left with open parentheses x minus, and
Let's see.
there we go. It's going to come. There we go. Open parentheses, and then x minus 3 pi. And then close those parentheses, and another close parenthesis plus 4. And now, once we have it in this form, we can list our transformations. And so, looking at our transformations, it appears that we have 5 transformations off of this sinusoidal function. It looks like we're going to go 3 pi units to the right. It looks like the 1/3 will cause a horizontal stretch by a factor of 3. And then those 2 transformations are going to be affecting our x coordinate, if you will, on these pre-image points. And now for the other 3 transformations, we have our 6 in front, our amplitude, so that's going to cause a vertical stretch. The negative will cause a reflection of the x-axis, and then our plus 4 will cause a translation up 4 units. And so what we're going to look at is we're going to look at inside of a list. So we will go to the edit number 1 there. And so Katie had preloaded these pre-image points just so that we wouldn't have to take the time to load those up. But those are in L1 are the points -2 pi, -3 pi over 2, -pi, -pi over 2, 0. And then we have pi over 2, pi, 3 pi over 2, and 2 pi. And then the L2 are the y coordinates of those points. So if we think about this, there was 2 transformations that changed the x coordinates. We had movement that was 3 pi units to the right, and we also had a horizontal stretch. So to use our calculator, we're going to go up to L3 here, and then once we're at the top with an 84, we can press enter, and that will allow us to go down to the input where the cursor is blinking. And there was 2 transformations here. We said one of them was to add 3 pi, so we'll take 3 pi. 3 pi. And then we're going to add, and we had a horizontal stretch. Our B number, if you will, was 1/3. So that means that all of these X coordinates are multiplying by a factor of 3. So we'll take 3 times L1, 3 times L1, and enter. And these should be the X coordinates of our image points. And now we're going to do a similar type of thing with the Y coordinates. And so we'll go to L4. We'll press enter. With the Y coordinates, we had 3 transformations that affected those. One of them was a vertical stretch by a factor of 6. So we will actually, we also had a reflection of the x-axis, which was a negative. So we can kind of combine those. So we'll put a -6 times, and our Y coordinates were in L2. And then we also had a translation 4 units up. So we'll put a +4 and enter. And these should be our new Y coordinates. And then from there, we are going to graph these 9 image points.
So right now we have L1 and L2 showing in our stat plot.
That's right.
So I should change these to L3 and L4, correct?
Correct. L3 and L4. And then once we have those, we will do a zoom stat number 9. And now we have our image points. And if we take a look at y equals, I think that was the original equation that we had.
It was the one with the factored out 1/3 B value. Yep.
Yep. And it should be both. Both of them should be exactly the same. These are equivalent expressions. So if we turn it on, I think we'll see that the black one goes right over top. And then I think even a nice little touch that I like to show to students sometimes is if we go to y equals, and we didn't show it here, but on Y3, Katie, can you type in the parent function cosine of x? And we won't graph this one, but maybe just turn that one off.
And we're
And
toggling these on and off. If you weren't aware, we're going on top of the equal sign and just pressing enter. And so it'll allow us to toggle them on and off. So right now that one's off.
And then if we go down to Y4, we'll do this using just our function composition, if you will, notation. So in this case, we have -6. And then our parent function was in Y3. So we're going to call up Y3.
And there's a couple ways of doing that. We can go into our variable button right here, or we could do alpha and the trace. We get sort of shortcut keys in there. I personally go into my variable button just because I know it's a variable, but other people like the shortcuts. I'm just going over to the Y bars and I'm going to pull up function Y3, you said.
So that was our parent function, and then open parentheses, and then our input, it was 1/3 x minus pi. And then we'll close the parentheses, and then we had a +4. And this graph should also be just another equivalent form, but just using the function composition idea. And let's see how that looks. And there it is.
So this really allows us to look at those equivalence relationships. The table itself, I've been using tables and graphs and equations, of course, with all of our polynomials, rational functions, looking at those transformations. But the table allows us to see when we change an x value, when we change our input variable by 1/3 as our b value, what happened to it? What happened when we subtracted that 3 pi, or added that 3 pi and that translation factor. So it's giving us that visual within a table. And so the multiple representations, we talk about multiple representations, obviously, in this course. We're allowing the students to see those multiple representations with a table, with the graph, with the function itself, and really hitting home on the connections between them.
Very good. Thank you, Katie. And I think we're going to do one more of these. It's pretty similar to how this one worked. And this next one we're working off the parent function tangent. And you could also do, the inverse functions would work basically the same way: cosine inverse, sine inverse, tan inverse. You could do the secant, the cosecant, any of these, but we're just going to do one more here with the tangent function. So Katie has set this up so that it's a little bit quicker here with the pre-image points. And so as far as the pre-image points for tangent, point A, if you will, I like to call that negative pi over 4 comma negative 1. Katie, you want to talk about how you created this program maybe real quick?
So the program is just there so I don't have to type in all the data points. So it allows me as a teacher to have control and make sure that my students are all getting the same data sets if we're looking at data sets. That way we don't have unequal size lists and get some sort of syntax error, some sort of error message. All it is I entered the data and said store, my angles into L1, and then I entered the data for my output values, so the values of tangent, in this case, only 3 of them, and I told the program to store it in L2. And so when I'm pulling up this program, it literally is just, I did also have it clear the list at the start. So it cleared any pre-existing lists, and then it's just putting in the data for the angles in L1 and the trig values in L2. So it's a super simple program. There's nothing fancy to this one, but it allows me as teacher to have control and get all my students on the same page at the same time, and kind of quickens up that part of it.
All right, very good. Thanks, Katie. And then, so the 3 pre-image points we're looking at are negative pi over 2 comma negative 1, and then the origin 0 comma 0, and then the point in quadrant 1, which is pi over 4 comma 1. I also like to think of this as 2 other locations. I call them pre-image locations. In this case, the vertical asymptotes. So I like to call it XL, which is negative pi over 2, and then XR, which is positive pi over 2. And the way we're going to work this is that's going to be like our X minimum and our X maximum on our viewing screen. So now if we go into Y equals, let's go ahead and clear all that out. And let's see, Katie, it's already in plot 1, right? I think.
We have our cosine.
Okay, so we're going to have to,
yeah,
okay.
so I'd have to change this to L1 and L2.
L1 and L2, there we go. Beautiful.
And then our window, we said we want negative pi over 2 to pi over 2 as our X min, X max. So those are our 2 asymptotes that we're looking at, and a step X scale of pi over 4. We'll just do negative 2 to 2 for right now. And I apologize, I can't see the chat when I'm sharing, so Todd, yell at me.
Yeah, I'm following it, Sarah. So
awesome.
Yep. Okay, and then from there, let's see. I think it does show the 3 pre-image points there. Let's take a look. There it is. And then if we think about how that graph of the tangent function looks, it kind of looks like that odd positive, if you will, polynomial function.
So I can graph it through those.
There we go. And so we're in good shape. And so we're going to do a transformed function. So this transform function that we're going to look at, and we're going to basically do the same approach that we did on the sinusoidal. So the equation we'll look at will be 1/5.
And we're purposely looking at different values for our A, B, C, D. I just want to point that out so that we can see the difference in the transformations. So this time we have
exactly
an A value that's smaller than 1.
So if you think about transformations, there's basically 10 of them. And so we did 5 on the last problem, and now we're going to do the other 5 on this one. So we'll do pi over 2.
Do we want to do negative pi over 2?
That's right. We're going to do negative pi over 2. Thank you. I forgot to write that.
Oops, and for some reason I didn't grab my fraction key, but that's okay.
And then minus 2x, and then close parentheses, and then minus 1. And so again, kind of looking like what we did last time. We'll start with some factoring on our B value. In this case, we kind of turn the two terms around. So what we'll do is we'll factor out the -2 inside of the tangent there, and a -2, open parentheses, and that's going to make this then x plus, and this will be a pi over 4. And then a close parentheses, another close parenthesis, -1. And again, now as we take a look at it, we've got our 5 transformations. If we think about the order of transformation, it looks like we're going to move pi over 4 units to the left. We're going to have a horizontal shrinking. We're going to have a reflection of the y-axis. There'll be 3 transformations that change the x-coordinate. And then the y-coordinate gets affected by the vertical shrink and also the 1 unit down.
Let's
So
change the color of our graphs so that we can see a difference between them.
perfect.
Two black graphs right now.
And then from there, let's go back to our stat, and we'll use those pre-image points. So in this case, the L3, the transformations that affected the x-coordinate, I think we said that we were going to move pi over 4 units to the left. So we're going to multiply by -2. Good. Let's do that.
Sorry.
-2 times L1. And then we're going to move pi over 4 units to the left. So minus pi over 4 units to the left. And that should take care of our new x coordinates. And then for the y coordinates, we'll go over to L4. And on this one, we had a vertical shrink, so we're going to multiply 1/5 times L2. And then from there, we're going to subtract 1. We also had a -1. And so those are the new image points. And then the other thing that we want to adjust is we want to fix our x min and our x max, which we'll do that in a little bit. We'll do that right after we do, I think, a Zoom number 9. Will that work for us, Katie?
Oops. I've got to go turn on our graph with
there we go.
L3
yep.
and L4 points. Yep. Okay. Would you like me to turn off the parent function?
Yes, let's turn that off as well.
Just go disable this one. You want me to leave those other 2 on?
That'd be great. Yep.
Okay, so Zoom stat. And all of this again can be done on Nspire as well. We're just choosing to use 84 here. We want to make sure we show some of that. So some of the features that
let's see here. Let's see. Did we? I think maybe we did something. I don't remember, but it should have gone right through our points here. Let's see here. When we did this the other night, it certainly did. Let's see here.
I have a feeling it's because I typed a minus pi over 4 for our horizontal translation, possibly.
Okay.
I'm going to go change my L3 here. Fill this out. So we had a -2. We had our reflection over the walk.
So you know what it was? It was, Katie, it was a horizontal shrinking. So we had to multiply by -1/2 there. Sorry about that. I didn't catch that.
Good catch. Good catch. Sorry, let me change that. So I'm just going to put -0.5 for time. -0.5 and then times L1, correct?
Yep.
All right. And then what was the rest of it?
And then it was plus pi over 4. Horizontal dilation. Perfect. Thank you, Rebecca.
I just typed in the wrong thing. I apologize. I pressed enter way too soon. -0.5 times L1 plus pi over 4.
Plus pi over 4. Yep. Pi over 4 to the left, and then we had a horizontal shrinking by a factor of 1/2. And let's see, did it work this time? Let's hope. There we go. Okay, now it worked. Okay.
Thank you all for our patience.
Well, that's okay. I mean, the same thing happened literally yesterday in my class. I mean, we had made a mistake, and it wasn't this problem, but it was something like that. And
It just reinforces that. I think those mistakes happen, and I think it's a great time to reinforce what those parameter values do. I mean, we might see that -2b value and think, oh, we need to multiply by -2, but no, it's actually the reciprocal. So I think it is a great opportunity for us to have those discussions with our students and really reinforce those transformations.
so Beth, you asked a good question about, don't you have to add pi over 4 before multiplying by 1/2? So yes, and certainly if it's doing it by hand, definitely I would want my students to be doing that first. But with the technology, it doesn't really matter. The technology is going to know to follow the order of operations, and so that's why it worked like this. And all right, so I think that's going to do it for transformations. So thanks, Katie.
Yeah, no problem. So really just kind of, again, hitting home on the use of the technology, using the table, using the function, the multiple representations, obviously with the graph, and really just making those connections. Transformations are huge, obviously, with this AP Precalculus curriculum. So starting it with polynomials all the way to the end until the test. So
For sure.
really kind of honing in. And you could certainly do, I think I saw a comment earlier pop up just briefly on my screen of, you know, would you do all these at one time? I don't do them all at one time with my students. This is, you know, a progression with them. So really that learning experience and taking our time to develop it through. Were there any other questions, Todd, that needed or comments needed addressing
Let's
from
see.
the chat?
I
I
didn't
couldn't see
see
the chat.
anything.
Every once in a while saw some comment pop up on my screen, but it was hidden for a while.
All right, so that's all I caught. So
Okay, fantastic. All right. So the next thing we're going to look at is we are going to look at some data that I collected. I used Nspire. You can certainly do this on the 84 as well. I just happened to use my Nspire to do some data collection. I was using a motion detector or CBR2, and I was collecting pendulum data. So I do data collection frequently throughout my courses for different uses, for different courses, of course, looking at curriculum, and it also allows us to look at transformations in that case as well. But this was pendulum swing data. So the setup on this activity is I had a motion detector. I had a student, or really my husband at the time, holding a pendulum that I had created just out of a washer, like a metal washer on a string. And I had him start that pendulum and then get out of my way as I collected the data using Nspire. So he was my little guinea pig of starting it and letting it go and getting out of my way and letting me do my thing. And so it collected data. I'm going to show you the data here in a second. It collected data that represents the distance that the pendulum swinging was from the CBR. So think of my CBR as being steady and my pendulum's going back and forth. And so it's collecting the distance from the CBR, from the motion detector, over time. So you've got distance on your y-axis or your output dependent axis, time on your independent axis. And when I do this with students, before we ever run it, I might show them just what a pendulum is, but I have them predict what is it going to look like. I think it's really important for students to connect their general sense of what data looks like, whether they're walking in front of a motion detector or whether they're riding a roller coaster, whatever it might be. When you're talking about variables, having them try to connect it with their own thought. And being wrong is totally fine. Those predictions are really important to solidify the concepts at hand. So I have them just do a quick sketch, or, you know, on a whiteboard, sketch out what they think it's going to look like, and then we do the data collection. So this one I did do with my husband, just because obviously I'm not at unit 3. I'm still in unit 1 of my own course. So I'm not quite ready to do this with my own students yet. I did it in the past with my pre-calculus students a couple of years ago when I taught regular pre-calculus, but it's been a couple of years since I did it with my own students. So this is our data. I'll pull this up. Like I said, I have it on Nspire, but this could just as easily be done on the 84. So Todd, are you able to see my screen?
Yep, you look great.
Perfect. All right, and you all will get these files. So this TNS file, even those two tiny little programs for the cosine and the tangent data, you all will get this when all the files get sent out. So on the second page, this is my data that was collected. So this is using our motion detector. And we can see here, we've got the position or the distance along our dependent axis. This is in meters, and we have the time in seconds. And so we can see what's happening up and down, up and down. And so the distance is increasing as time is increasing. So thinking about that change in tandem, as our time increases, our distance increases, and then it decreases and it increases, and we go back and forth and can see that periodic data. Now, if you don't have motion detectors, you could certainly just put in some list of, sunset over the day of the year. Sunset times or tides from the ocean, things of that sort. So lots of different ways of using sinusoidal data. So the idea here is that we can come up with a model that fits this data. If I trace along, I'm just going to click on my screen because I've got the data on there. I could just as easily be on a data and statistics page. I can come up with an idea of where my midline is, which would be that p value. If you think about your sinusoidal parent function with a, b, c, d in there. So your midline, we can visually kind of get an idea of where that might be and what it means. So it's about 2. You can see that here. Oh, sorry, about 0.2. If I can read my own screen. Our midline looks like it's about 0.2. So that's when my pendulum is right there smack in the middle. So if I've got my motion detector steady and that pendulum is going back and forth, that would be the distance from the motion detector when my pendulum hits that middle point, when it's not close enough, not far enough away. We can do a little bit of estimation here on what our A value is, what that vertical stretch factor is, or vertical shrink factor. So that vertical dilation, or our amplitude as we usually call it when we're talking about trigonometry. So if I look at my screen right now, I am currently over here at a time of 0.55 seconds. I was my furthest distance away at 0.285. So that means that my that my A value is about 0.085, if I did that math right. 0.085, that's my A value, because I said my midline was about 0.2. And that midline may be a little higher, maybe a little lower. If I wanted to figure out my horizontal translation, if I wanted to figure out my C value, and I'm using my sine function, then I need to kind of look at where that midline is. I've got to come back here a little bit. And I'm sort of estimating at this point because it's not going to get real precise. I don't have enough data points. I'm sort of estimating where am I hitting that midline and moving up to its maximum if I wanted to talk about a positive A value. So at what time, again, it's referencing those variables. We're thinking about those transformations. I can see that I have transformed or translated to the right, and it's about 0.3, maybe a little bit more. If I went to the right, it gets 0.35. So I would say that my C value is about 0.325. And I'm jotting down these ideas. I've got a little piece of paper next to me, so I'm jotting down these numbers so that I can come up with my model. I'm sort of doing this eyeball fit of a model before I run a regression. So when I do data with my students, I'm always having them eyeball fit. I'm always having them come up with what they think those parameter values are, thinking about those transformations before we run regressions, because I want to compare the two. So far I've come up with my A value. I have my D value, my midline written down. I've got my horizontal translation. I just need my value of B. So if I look at how far apart my maximums are here, my relative maximums are, this one is happening about half a second, 0.5. I'm looking at the time over here on this left-hand panel. This maximum point is happening about 0.5, and the next one happens maybe 0.55. I moved a little bit. And the next one I'm just kind of arrowing over is going to happen whoops, about 1.55. So it looks to me like it's taking 1 second to repeat that motion. It's taking 1 second for my motion, my pendulum, to get the furthest away from the motion detector, come back as close as it can, and then go back. So I've essentially figured out that my B, so that would be my period right there, is 1 second. So my B is going to be right about 2 pi. My B value is right about 2 pi. I kind of got lucky, I think, here on this one. that was easy math. That was easy math there. So my B value is going to be about 2 pi. The reason I'm pointing this out is because on Nspire, and again, you could do this on 84 in your Y equals, I can go into my menu and I can go to analyze, and I can type in that model that I just came up with. So before I ever run a regression, I can see if my model and my knowledge of my transformations, my knowledge of what this means with the physical sense of a pendulum swinging, or ocean tides or sunrises, sunsets, things of that sort, I can see if I have the right idea down. So I'm just going to type in what I just found. My A value is about 0.85 times. I'm using the sine function. I found my B was 2 pi. Need that pi button. Oops. And then I had X minus 0.325 was that horizontal translation to get from the midline and going up towards the maximum point. Tell me if you think I typed this in wrong. And then 0.0, where did it go? 0.02 was my approximate midline. So I'm typing it in. I'm just going to go ahead and press enter one more time. It's just saying, does it want me to set it? Yes, I want it to set. And now we can see that was a pretty decent fit. Not perfect, because again, I was estimating. I wasn't using infinitely many points to estimate from. It's not going to be perfect data, but I got a model to fit it. And from there, I'd want to compare it. So one of the things that we're doing in our AP Precalculus course is using regressions. And so looking at those regression models, I'm going to go ahead and run that regression here. Just going back into my menu, analyze. And this time I'm going to do my curve fit, and that was a sinusoidal curve fit. And I could run my regression on a data and statistics page, which I'll show here in a second so we can see the residuals at the same time. So here you can see on the screen our sinusoidal regression function. And this one does come, if you notice on the screen, you can see the format. It has A times sine, and that B value is not factored out. So kind of keeping in mind the equivalence. So we talk about equivalent relationships, obviously, throughout this course. The B value that I typed in was factored out. And so, comparing the two and having my students compare the two would be handy. Just are they equivalent? And then visually, we can see, and unfortunately I have mine in the same color, but you can see two different curves there. I pressed the wrong button. You can see this dark one, this really bold one, that was the regression fit right there. So that one is the regression fit, and I'm just kind of clicking on my screen, which is why we have that. We can also look at the regression within a data and statistics page, because this data is stored as lists. And my list had names, which is really handy on Nspire. Again, you could do the same thing on the 84. For this is a data and statistics page, I'm going to set my time as my independent variable. And I'm going to go and set my position as my dependent variable. And so I could do my regression here as well. The nice thing about this regression is that I'm going to be able to then look at my residuals. We show that sinusoidal regression. We can see that equation right here. Also, again, that B value does not appear to be factored out. So it's keeping that same format as the previous page that we had. But we want to look at the residuals. Was it a good fit? What does it mean to be a good fit? So if I go down to menu and analyze again, I can go down to residuals this time and show my residual plot. It's going to split that page. And typically we look for, like, is there a pattern? Like, we don't necessarily want to see a pattern, but we do see pretty equal amounts above that horizontal axis and pretty much equal amounts of data points below. So to me, that looks like a fairly good fit. It's not going to be perfect. Data often is not perfect, but we do get that sense of what do our parameters mean and how can we use them. Todd, do you have anything to add to this before I go on to looking on the graph page?
I would just say with this residual plot, with sinusoidal regressions, notice that a lot of times these things, they look like sinusoids themselves, and that's okay. In some of the summer institutes we did this summer, we had people that contacted high-level stats people, and so what's the meaning of this residual plot having a sinusoid? And a lot of the responses from the high-level stats people is that it's just not that meaningful. It's not that useful. And so with a lot of the other regressions, exponential and polynomial, that residual plot's a big deal. And here, it's just, many times, it's just going to be its own sinusoid, which is okay. And so we shouldn't have to panic about that.
Awesome. All right, the last little part we wanted to look at with this same activity was, we've got this equation. Well, so what? One of the things we do talk about in this unit of trigonometry is solving trig equations. And so we can use this function, a regression function, to solve an equation. So if I wanted to find, I'm going to just open up a graphs page here, just a plain graphs page. One thing to notice is that we are in function mode. That's great. We are going to look at the function. I want to show my data though. I want to show, well, specifically, I want to show my regression function. So that regression function, whoa, I don't think that was what I meant to have. There it is. There's that regression function. It was already in there. So here is that regression function. I just went up to f1 of x. I'm going to turn that on. It doesn't look very pretty right now. So let me do a little window adjustment and do a zoom trig. And I need to change my y values. I need to adjust those y values to be negative. I'll do 0.5 to 0.5. That should be good, I think. There we go. Nice. So I might want to see, at what times, and maybe I adjust my x's, but at what times, we've got this swinging pendulum. When was that pendulum, I don't know, like 0.25 meters from the motion detector? So one way that we can use our technology is to solve the equations and thinking about what does it mean? So if I'm looking at this pendulum is swinging, it's going back and forth, at what time periods or at what intervals of times was this pendulum 0.25 meters from the motion detector? I can graph another function. So I can just go into my next function there and put my 0.25, my horizontal line, and look for those intersection points. So I've got these two functions. I've got my horizontal line that represents 0.25 meters from the motion detector, and I've got my sinusoidal regression on there, or maybe it was my model fit that I could have used as well. And I'm looking for when are these intersecting. So looking at the intersections, and again, this is something that we can do on the 84. I just happen to collect this data on Nspire. So I can go and I can analyze for those intersection points. I would want to tell it one at a time. And if you're on the 84, you're going to just go click those two functions and then put in your quote unquote guess. On the Nspire, I am clicking to the left and the right of an intersection point, and it gives me that value. So I can see that the first time when I collected this data, so between the 0 and 5 seconds I was collecting, the first time that my pendulum was 0.25 meters from my motion detector, was at 0.2425 seconds. And we're able to get this idea with our cyclical data that we do have multiple solutions, that it's not just one answer. And so from a teaching standpoint, from a testing standpoint, as well as how can we use the technology to solve equations? Well, this is a great way. We have two intersecting functions. We often don't think of the y value, the 0.25, as a function, but a horizontal line is clearly a function, and we're looking at the intersection of them.
You know what, Katie? I think we can use this same question to solve an equation, because that's kind of where we're going next.
Absolutely.
So let's find all solutions here from 0 seconds. Let's not go all the way to 5 seconds because we've got quite a few solutions. How about if we go from 0 seconds to 3 seconds?
Sure.
And so
how would you like me to approach that?
So maybe we just fix our window a little bit.
All
So
right.
we'll go from 0 there for X minimum.
Right.
And then for X maximum, we'll go to 3. And now it looks like we can clearly see that there's 6 intersection points. And I think one of the big benefits on solving equations with Nspire is we can use geometry, and we don't have to do that intersection 6 different times. So if we go into menu, and then we can go number 8, geometry, and then we'll go to number 1, points and lines, and we can do our intersection points, number 4. And it's going to ask us which curves we want the intersections of, so it'll be our sinusoidal right there, and then our linear. And it's really busy. They're really close together. But
just separating them out. There we go.
Really nice. And then we can kind of see that our first point that you said was 0.425, and then that was on the way up of the sinusoid, if you will. And the next time that it's on the way up looks like it's at 1.43.
Yep, right.
And I think that's a nice way that we could actually find the length of the period. And you kind of estimated it before that it was around 1 second, and that kind of verifies that it's pretty close to 1 second.
Right, and I pulled down that last one, or the second to last one, the 2.43. Again, there's that 1 second. If you look at those other ones on the top, with the exception of this first one that I typed in, the other one's 0.275, 1.72, 2.72. Absolutely, just connects it back to that idea.
Super. So Katie, we're almost out of time. Do you want to just maybe show the little bit of the polar?
Sure, no problem. So the polar rates of change, and you all look at this file, is looking at having a polar function graph for us, so 3 cosine 2 theta. And we are going to look at the average rates of change over the interval from 0 to pi over 4. And what we have control over here is actually the angle that's going to change. So Todd, do you want to talk about what's on the screen real quick before I?
Definitely. So we have R1 of 0. So we're starting at angle 0. And then as Katie presses this slider, this is the angle that's changing. And so what's happening is the average rate of change, or the AROC, if you will, is going to be changing. And so it's talking about our new radius versus our old radius. And it looks like we've got some negative numbers here, meaning that the new radius is smaller than the original radius at angle 0. And I think this is a really cool visual, because we can kind of see on these line segments, these black line segments are the actual radius of this rose curve. And
so those rates of change are decreasing. So they are negative and they are decreasing. I'm just going to go back to that 0 there to show that effect there. So it gives the students a visual representation of that decreasing rate of change. And a lot of times we think, I mean, obviously with polynomials, we're thinking about that decreasing rate of change as concave down. Different here.
Completely
With
different.
our
Yeah,
polar functions, but giving them a visual for rate of change on a polar graph. And so this
exactly.
activity that you all will get, this is on Nspire. This is not one that I would say, at least with my knowledge of coding, I am not a major coder. I have not seen this done on 84s or anything of that sort. So this would be strictly an Nspire activity.
Edward, you asked about could we see a cardioid on the exam? I would definitely think we could see a cardioid. We could see a rose. I don't think students are going to have to know what the type of curve is by the equation, but I think it's going to be more conceptual.
All right, and I believe we are out of time. I wish we had more time to share with you all. We had a couple activities planned, so we apologize for not getting through it all, but how it is an hour. And
Time
Donald,
flies when you're having fun.
Donald, you're muted still.
Thank you. I just want to remind everybody that the files will be sent next week via email. And our winner of the door prize is Miss Sarah Browning. So Sarah, someone will be in touch with you to find out which technology you'd like to receive. And again, you'll get a certificate of attendance and the files for all the sessions next week. They'll be emailed to you.
And thank you all for coming on. We hope you enjoyed the rest of your weekend.
And I would just like to say, if any of you have questions, feel free to contact either Katie or myself, and we're definitely would like to share any information that you, any questions that you have about this. So thank you very much. We enjoyed it.
Absolutely.
Thank you guys.
Thank you all.
Very good.